Hello and welcome to this video lesson. In this video lesson, we will be looking at circuit analysis and we will be looking at circuits with medium difficulty. We got a mixed circuit over here. We got a circuit in which we got a battery is connected to a resistance here, and then we got a wire that splits into two sections. We got one section which is going to a 10 ohm resistor, and we got the other section which is going into a 5 ohm and a 15 ohm resistor, and then it connects back to the battery through a wire. The information for the circuit is all written here, and we're going to try to find all the information that we can for it, including the potential differences, the current and the power, and the equivalent resistance as well for the source. We're going to use two different methods of solving this. First one is going to be using equivalent circuits, and the second one is going to be using Kirchhoff's voltage and current law, and you can kind of decide on which way is the best way for you. When solving circuits, the first thing we want to do is to find any information that we can right away. In this case, we got the current and the resistance, meaning that we can find the potential difference across resistor 1, and we can find the power as well. Let's do that. Voltage across resistor 1 is going to be equal to the current across resistance 1 multiplied by the resistance in there, so that's 3 times 25. This is going to equal to 75 volts. Write that right here. And the power at 1 is going to equal to I1 V1, which is 3 multiplied by 75, giving us 225. And we'll write that right here. Now let's kind of figure out what informations we have. We know that right here the potential is going to be 0 for my electrons, so 0 volts here. It's going to gain a certain amount of energy. I don't know exactly how much. I do know that it's going to spend 75 right here. And that's kind of all I know. So I don't know exactly how much energy it's going to gain here because it's going to have more than 75 because it's going to spend 75 here and some more across either this resistor or in the combinations of these two resistors to get 0 potential back here. So I don't know exactly how much, and that's kind of what I need to calculate. I don't have enough information to know the potential differences across these resistors yet, and I have to come up with a strategy to figure that out in order to solve everything for my circuit. Let's use the first method, which is equivalent resistance, and then we're going to use Kirchhoff's law for the second method. Whenever we have only resistors and only one battery, probably the most efficient way of solving the circuit is equivalent resistance. So let's do that. So to find the equivalent resistance for this circuit, I'm just going to do this combination here and see if we can solve the circuit based on that. If we can't, then we're going to actually go ahead and combine everything. To combine these set of resistors, we know that these two are in series, so we can add them up to find this resistance. And once we have that, we know that this and this are actually in parallel, so then we can find the equivalent resistance of 2, 3, and 4. I'll redraw the circuit here. And we're going to have one resistance here, that's resistance 1. And then we're going to have a combination. We're going to keep this as resistance 2 for the first step, and we're going to have a combination of resistance 3 and 4 here. I know for resistance 3 and 4 they're in parallel, so to find the total resistance I have to add resistance 3 to 4, and that's going to be 5 plus 15, and that's going to give me 20 ohms here. Now I want to get an equivalent resistance here, and to add those up, I have to add them in parallel. So I'll redraw the circuit again. So I'll have resistance 1 here, and I'll have one resistance instead of having those, and I'm going to have resistance 2, 3, 4 all combined. So because they're in parallel, then 1 over resistance 2, 3, 4 is going to equal 2, 1 over the resistance of 2 plus 1 over the resistance of 3 and 4. So this is going to equal to 1 over 10 plus 1 over 20. You can do this in your head, or you can do it on a calculator. You should get 3 over 20. And I need to take the reciprocal of that to get R2, 3, 4 is going to equal to 20 over 3. Now that I have this is actually very helpful because I know that I have resistance 1 here, which is 25. I know that resistance here is 20 over 3. I know the current that's coming out of my battery is 3 amps. And I've already have the voltage drop here. Now I can find the voltage drop here, which is the same amount of voltage drop here and the total voltage drop between resistors 3 and 4. So to find this, I simply have to find, I know the current and I know the resistance, so I can find the voltage drop. Voltage drop across resistance 2, 3, 4 is going to equal to the current there. The current here is same as so the current isn't changing across this wire here. So the current here, which is in resistance 1, is 3, and that's going to equal to the exact same current here. So I'm going to use I1 and resistance 2, 3, 4. And it's going to equal to 3 times 20 over 3, which is just 20. And since this voltage drop is exactly the same voltage drop or potential difference from here to here, that means that this resistance, because it only has one resistor here, is going to experience potential difference of 20 volts. So I'm just going to write V2 here is going to equal to 20, and that's an additional information in my circuit here. Now, with this information, I can start finding the current across 2. So I2 is going to equal to V2 over R2. That's 20 over 10, which is 2 amps, and this is 2 here. And the power across 2 is equal to its current multiplied by the potential difference, and that's 2 times 20, which is 40. So I'll put that value here as well. Now that I have current here and I have the current here, I can use Kirchhoff's current law. So I'm going to take this to be junction 1. So at junction 1, current 1 is going to equal to the current on resistor 2 plus the current on resistor 3 or 4. It doesn't really matter. They're the same current. So 3 amp is going to equal to 2 plus current 3. So I3 is going to be 1 amp. And I can put that value over here. And resistor 4 is going to have the same current because it's going through the same wire. Once I have the current here, I'm not going to write how I'm going to do the calculations for voltage 3 and voltage 4 here. I know that the voltage is going to equal to the current multiplied by the resistance for both cases. So 1 times 5 is going to give me 5 here, and 15 times 1 is going to give me 15. And if I add these two up, I will get 20 across potential difference of 20 from here to here, which is the same potential difference as resistance 2, which should be the case, which is fantastic. You can also find the power for these two. The power is going to be the voltage multiplied by the current. If I do the multiplication, 5 times 1 gives me 5, and 15 times 1 gives me 15. Let's figure out the total potential difference across the battery or the EMF. In this case, we know that we're going to have zero potential here. If it's zero here, that means it's zero everywhere until this point over here. We know that there's 20 volts difference here. So that means at this point we need to have potential of 20. So I will add that set of information here, 20 volts. And I know that there is 75 potential difference here. So in here we should have 95. And just to do a very, very quick check, that 1 coulomb of charge is going to come in. It's going to get 95 joules of energy here. It's going to spend 75 here. It's going to be left with 20. And then it's going to spend the 20 over here, come to get and have 0. And it's going to go back, get 95, spend 75. It's going to instead, let's say, instead of going this path, it's going to go here. It's going to spend, for resistor 2 is going to spend, sorry, for resistor 3 is going to spend 5 here, so it's going to be left with 15 here. It's going to spend another 15 here, so it's going to have 0, and it's going to go back to the battery and gain some more energy. This is fantastic since I know that there's 0 potential here and 95 here, so the total potential here needs to equal to 95. And for the current, I know that the current isn't going to change from here to here because it's the same wire all across here. So current here is 3, that means my battery also has a current of 3. And to find the equivalent resistance here, all I have to do is I have to divide the potential difference by the current, which is 95 over 3. I'll write it as fraction in this case. And to find the power, I have to multiply the voltage or the potential difference across the source, which is 95, by the current, and that will give me 285. To check, one way of checking to make sure that my solution might be correct is to make sure that all these powers add up to the power here. I have 225 here. I add 40, I'm going to get 265. I'm going to add another 5, I'm going to get 270. And I'm going to add another 15, I'm going to have 285, which is the power provided by the battery source, or the energy that's being supplied every 1 second. And that's exactly what I have, which means that my analysis is very likely correct. In summary, whenever we have a circuit which has a lot of resistors, especially if it's a mixed circuit, then equivalent resistance is a fantastic way to find information about it. Usually in these questions where we have a lot of resistances and not enough current values, then combining these will allow us to kind of make a smaller circuit. And if we have even one set of information about the current, or then we can figure out potential differences across different regions of the circuit. In this particular case, we found that we had no idea what the potential difference across here and here were, but we did know how much the potential difference here was. So by combining these, we were able to put these all into one resistance, and knowing that there was 3 amps of current flowing out of the battery source, we were able to figure out what the potential difference across this region was. Once we had that, we figure out that we can figure out the current here, and using Kirchhoff's current law, we could find the current going here, and therefore voltage here, or potential difference. And once we have that, we could also find the potential difference across the battery. We could have done that earlier as well, but again, there's so many different ways of solving this, and by combining them, it will really, really, really simplify our question to a more manageable state. Now, let's go back to where we had found all the information that we could from the circuit just by looking at it, and let's use the second method of solving this question. One other piece of information that we do have that I forgot to write here is that the current across the battery is 3 amps because the current in this wire doesn't change. and that's 3 amps here, meaning that it's going to be 3 amps here as well. Next, I'm going to write all the equations that I can based on Kirchhoff's voltage law and the current law. So to start with Kirchhoff's voltage, I'm going to divide this into 2 loops. One loop is here, so loop 1. That's one path that the charges can, or an electron can take. Electron can come through the battery source, go here, and it can choose this path, which is through resistor 2, and go back. And the other loop, which is going to be loop 2, is when it's going to go through this path. And I will label that with a different color. Let's use orange. So it can come here, go through this loop, and come back. And this is going to be my loop number 2. Kirchhoff's first law says when electrons come here, they have to gain a certain amount of energy, and they're going to go and they're going to spend it here, they're going to spend it here, and they're going to come back and do that all over again. So the energy they gain is going to equal to the energy that they lose in the loads. So basically for loop number 1, the EMF, which is the energy from the source, is going to equal to the voltage drop across resistor 1 plus the voltage drop across resistor 2. And we don't know the EMF value, so I'm going to keep it as E, is going to equal V1, which is going to be current 1 multiplied by resistance number 1. And the other one, I'm going to label this as I2, so we do know that. And this I'm going to label as I3, and this is going to be I1. And if it goes through loop 1, it's going to go through resistor 2, so it's going to be I2, R2. And I'm going to put all the values that I know. So I know I1 is 3, I know R1 is 25. I don't know I2, but I do know that R2 is 10. I'm going to just rewrite this so that all my unknowns are on one side and all my knowns, 3 times 25, which is 75, is on the other side. So I'm just rearranging the formula here. Then I'm going to write all the information for loop 2. For loop 2, I'm going to have the current or the charges flowing through the battery, and that's going to equal to, they're going to go through and spend some of their energy on resistor 1, they're going to spend some of their energy on resistor 3, and some on resistor 4 before they go to the battery and gain some energy again. So E is going to equal to I1 R1 plus I3 R3 plus, and this is V4. And for the fourth one, I know that the current is going to be the same as 3, so I'm just going to write it as I3. I'm going to put in some values here. E is going to equal to I1 times R1, that's 3 times 25, plus R3. I know the value of R3 is 5, but I don't know I3. And I know the value of R4 as 15, and I don't know I3, so I'm going to keep it like that. And then I'm just going to rearrange this. 5I3 plus 15I3 are going to be 20I3, and I'm going to bring them to the left-hand side, so they're going to be minus 20I3, and they're going to also equal to 75. We can see that currently we have one equation from loop 1, which has 2 unknowns. It's got the EMF, or the potential difference across the battery, and I1, which is unknown. And we have the second equation, which has the EMF, and I3, which is unknown. So in total, I have 2 equations, but I have 3 unknowns. I need a third equation in order to figure out what all the values are. And to do that, I'm going to use Kirchhoff's current law. For the current law, I have to look at a junction. I'm going to take this junction over here. I can use other ones as well, but this is a very nice junction. I'm going to call this junction 1 or node 1. Completely up to you which terminology you use. And at junction 1, I know that current 1, which is coming in to the junction, is going to equal to the current out, which is I2 plus I3. I don't know what any of those values are. Actually, I do. I know that I1 is 3, and I2 and I3 are unknown, and I'm just going to rewrite this as I2 plus I3 is going to equal to 3. Now, once I have this, I have 3 equations, and in these 3 equations, I have 3 unknowns. Those unknowns are the potential difference across the battery, I1 and I3. This one doesn't have the potential difference. This one doesn't have I3, and this one doesn't have I2. But we have 3 equations and 3 unknowns, so we can start solving things. I'm going to write down all my equations here. So the first one says EMF minus 10I1 is equal to 75. The second one says the potential difference minus 20I3 is equal to 75. And my last one says that I2 plus I3 is equal to 3. Now, once I have these 3 equations, again, there's 3 equations and there is 3 unknowns. These are my potential differences. These are my I2s. I did make a little mistake here when I was writing it out. This, been making that mistakes all along. This is I2, this is I2, and this is I2. I have my I2 as unknown and I have my I3 as unknown. Then you can use math to solve this, but at this level of physics, I usually don't expect my students to spend time doing the math, and I do want them to just do the physics and come up with these 3 equations. That's the main thing. So my students, generally, they can use a calculator to solve this. I cannot provide methods of solving things with calculator because there are so many different types of scientific calculators, and I can't provide a tutorial for each one on this YouTube video. So you can learn how to solve 3 equations and 3 unknowns with your specific calculator. I'm sure you can find an instruction on your calculator or online. And once you solve this, so using calculator, you should get the EMF as 95 volts. You should find that I2 is equal to 2 amps and I3 is equals to 1 amp. And again, the calculator does this in no time, and again, this is a physics course, so usually I personally don't expect my students to know how to spend time doing the math. They should be able to do the math, but they shouldn't be spending the time doing the math. So EMF, which is the potential difference across the battery, is shown as 95. I'm going to put that value in. I2 is 2. I3 is 1. And I know that I3 and I4 are the same, so this should also be 1. Once I have this set of information, everything else is just using the equations, so I'll go through them very quickly. Here, to find this voltage or all these potential differences, I have to multiply I by R, so I'll do that individually. This one is 20, this one is 5, and this one is 15 when I multiply everything. And in terms of power, it's the same idea. I have to multiply voltage by current for each case, so I'll do that now. 20 times 2 is 40, 5 times 1 is 5, and 15 times 1 is 15, and 95 times 3 is 285. And finally, to find the resistance for or the equivalent resistance here, that's 95 divided by 3. I'm just going to leave it as fraction. 95 over 3, which should be the exact same set of values that we got from our last set of analysis using a different method. So you can use whatever method you want. There are so many different ways of doing this, and this is just two different methods of kind of going through it. But when you are using Kirchhoff's law, make sure that you draw the possible loops, and these loops kind of explain which way an electron can flow through the circuit. So in this case, loop 1 was this path for the electrons, and loop 2 was when it goes through resistor 3 and resistor 4. So once you have the loops, you're going to write the Kirchhoff's voltage law for those, and you're going to take any junctions that you have. In this case, the circuit was only split at one point, so I can use junction 1 either here or here. It wouldn't actually make a difference. If you had more junctions, so if you had another split over here, then you would have to write another junction as well and write another equation, and you'll have more unknowns. And in this case, once you have all of them, you can use math to solve the 3 equations and 3 unknowns, or you can just use your calculator to get the values. I hope this was a helpful tutorial for a medium level type questions for circuits, and I hope that you get to choose the best method that you like to solve these circuits.